In this lesson, we're going to take a look at Kepler's laws. Kepler's laws are pretty straightforward, and they describe the motion of planets around the sun. Now, technically, they work for any body orbiting another body. They describe the path of something as it orbits another thing, so it doesn't have to be a planet around the sun. It could be like the moon around Earth. But Kepler's first law of planetary motion actually describes the shape. It says orbits are elliptical in shape. So planets' orbits are ellipses with the sun at one focus. Now, what do I mean by focus? Well, an ellipse has two foci, and what they are they're the points where you can actually hook a string in order to draw an ellipse. So I'm going to do that here. I'm going to use these two here, and so these two suction cups on this board are acting like the focus for this ellipse. I'm going to take this string, and I'm going to hook it to this marker, and I'm going to trace out the path by keeping the string taut to those 2 points. When I do that, I get this elliptical shape. So it's not quite a circle, it's a stretch circle. And the sun is at one focus. So the focus here is this suction cup. And so Kepler's first law just says this is the shape that planets follow. And all of the planets have the sun at that focus. So if I were to grab a longer string and switch to this shape here, I would create another ellipse. And it's a little bit bigger. This one goes a little bit further out, but then it comes in close, and there's our ellipse. And so again, all of the planets, they don't necessarily have the same focus over here, but they do all share the sun as one focus of that ellipse. So we could have an inner planet and an outer planet. Those are the orbits that they have. Those are the elliptical shapes. Kepler's second law actually has to do with how quickly a planet moves around the sun. And it says equal areas are swept in equal time. Now, this also gets back to this shape. Okay? And so if I pick one spot, say right here, and I go some time later, say like 3 months later, and I'm over here, then the line we draw from the focus of the sun to the elliptical shape of the orbit, if we shade in this area, and this time is 3 months, then any other point that covers 3 months will have the same area as this shaded area. So if we're all the way on the other side of this, then we might say this area right here, this is also a 3-month time period as the planet moves from here to here. The area here and the area over here are the same. They're equal. And basically what this tells us is when the planet is closer to the sun, it moves faster, and when it's farther from the sun, it moves slower. So closer is faster. Now Kepler knew this, but he didn't know why. It actually took Newton's laws and his theory of gravity to explain what's going on here. And if you think about it, let's say the planet is orbiting around like this. As the planet is here, the pull of the sun's gravitational field is in this way. The planet's inertia wants it to keep it going this way. As it moves further and further along this path, this force is more and more in line with the direction that it's moving. And so that accelerates it. And so it gets faster, 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 and then as it gets over here, it's getting closer and closer and closer, and that makes that field stronger and stronger and stronger. So right here, it's getting pulled the hardest, and it's moving the fastest, and then it hits this spot, and it's going so fast it starts to fling away. And so now it's moving away, but it is moving this way, and the sun's force is this way. You'll notice there's a pretty big section of that that's pulling against the velocity of the planet there, and so it slows it down, slows it down, slows it down, slows it down. And here we get it moving at its slowest speed, and then it speeds back up, and then it slows back down, and it speeds. So when it's moving the fastest, it's the closest. When it's moving the slowest, it's the furthest away. Now you got to be careful here. These two locations have nothing to do with the seasons. I mean, the seasons are caused by the tilt of Earth's axis. And since we have opposite seasons on opposite hemispheres, northern and southern hemispheres, right here, it turns out this is actually winter in the northern hemisphere, and summer in the southern hemisphere. So we're moving by the sun a little bit quicker in the northern hemisphere's winter. But don't confuse these positions with having to do with the seasons. They do not. It is the Earth's axis tilt that causes our seasons. And then, of course, Kepler's third law is also related to orbits and time periods. Kepler's third law is actually a mathematical equation, and it says T1 squared over T2 squared equals R1 cubed over R2 cubed. Now the R is average distance. Okay, we can see that the distance between the sun and the planets is constantly changing since it's following that elliptical shape. R is the average distance between the sun and a planet. T is what we call period. And period is the time for one revolution. Time for one rev. Now, if we go around the Earth, or if the Earth goes around the sun once, we call that a year, right? It takes just over 365 days. And Jupiter's year is longer than Earth's year. And there's two reasons for that. Two. So we have this relationship, and we can use this if we know Earth's period and average distance. We could find, say, Jupiter's period if we knew the average distance, or if we knew how long it took to orbit the sun, we could figure out how far away it was. But really what I want you to get out of this is, as we get farther from the sun, the time it takes to go around the sun also increases. And there's two reasons for that. The first reason is this path is much longer than that path, right? It's got a bigger distance around because it's a bigger ellipse. So one of the reasons is the further away it is, farther away means longer orbit. The other reason is the speed, the average speed that these things have as they go around. If this was going as fast as this planet was over here, gravity wouldn't be strong enough to keep it in this path. It would just fling way far away and it wouldn't come back. If it was going too slow, it would fall into the sun. If it's going too fast, it flings out. And the faster it's going, the more force it takes to hold it in. If it's going too fast out here, the gravitational field is too weak. And so the other reason that it takes longer for the further away planets to go around the sun is because they move slower. They have a slower speed farther out. And again, Kepler was able to come up with these three laws just by observation. He's like, this is what it shows when we look at the data of the planets moving around the sun. But he did not know why. It actually took Newton's law of gravity to explain why these things were occurring.